Welcome to topic 8.5, electric flux, daily video number 2. In this video, we will apply the idea of electric flux to non-planar and closed surfaces. My name is Easton Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Before we dive into this particular video, let's do a brief review of what electric flux was. We had the dot product of the E field dot the area vector, which ended up looking something like this. But here's the key thing. This equation is only true if it's a planar surface, where the angle is constant for every single area term, and for that matter, the E field's constant for every single area thing. Basically, if all these things are constants, things are great. But if it's non-planar, that means we're going to be changing a couple different things. We're going to need something else to solve this. What are we going to need? Woo! Calculus! I'm excited. You're excited. Let's hop to it. So looking at calculus version of this one, we're taking the integral sum of the E field dot times all the little area elements that are in our particular surface. So just like last time, we have our electric flux, we have our electric field, but now we have a differential area that we're going to be looking at. So here's our surface. We kind of break it up into a bunch of little dA elements. We have our electric field that's traveling through, and we have our little dA that's kind of hanging out kind of like that. So this is what we're referring to in our picture. If I were to put an angle in there, once again, it'd be the angle between the electric field going through and that tiny little area vector that's there. But here's what makes this thing tricky. There's that area element, and there's that area element. And depending which one that I pick, the angles are going to change and do all that stuff. So conceptually, you need to understand, as it says here, that how this works, that the flux going through all those different surfaces is going to have to be the same. But you're only going to have to work with, for this equation, you're only going to work with ones that leave the surface at the same angle, so that this dot product doesn't vary as a function of dA. That's a good thing. Or if a surface area is defined by geometric shapes that do have changing angles, but you can very easily find what those shapes are going to be, whether it's a triangle or a cube or whatever that case might be. So let's look at one thing kind of conceptually for this setup. We have area 1, which is just going to be our planar surface, but then we have A2, which has the same outline, but has this weird little bump to it. Well, here's something that's really kind of cool about this. The flux going through A1 equals the flux going through A2. Conceptually, this is something that we need to make sure that we understand. Sure, the angles here are all going to be different on every single part of the surface, but every electric field that enters is also going to exit through that other one. So the flux is going to be identical, even if that surface ends up being curved. So it seems kind of weird, but it's totally true. So let's look at an actual example. In particular, we want to derive the total electric flux through a closed surface, such as a cube, with sides of length s, if an electric field of magnitude E passes through it perpendicular to one of those faces. If this is a question that was given to you, one of the first things you should do is draw a good picture. Drawing diagrams and having representations is essential to understanding physics problems. And I think you're going to see once we draw this, the answer might come clear to you. So we have our cube that we have there with sides S. We draw this electric field traveling there to the right. You could have it go any which direction, but straight through. You might say, well, how come it has to go there that way? It could go through one of these corners, but that'd be more difficult to solve. Let's pick a case that sends it straight through one of the sides, because that's going to be easier for us to solve for. Also, I'm going to have all these different surfaces. I'm going to have A1, A2, A3, A4, A5, and then A6. So remember, whenever we draw area vectors, they're always going to be outward from closed surfaces. By definition, that's how we define a surface. So with that in mind, I want to know what the total electric flux is going to be for this closed surface. Now, if you already know the answer, way to go you, but let's actually derive it, because that's what this problem ends up solving for. So if I looked for the flux, it's going to be the integral sum of all these different elements. Well, wait a second. Each one of these elements is just a square. So I'm going to have the E field through area dotted with area 1, E field dot area 2, E field, so on and so forth, with every single one of these elements. So every single one, it's just the sum, because that's what the integral means, is the sum of every single one of these surfaces. When I do this, I have to remember that E dot A is EA cosine theta, and remembering that cosine of 90 degrees is 0. Wait, so that's going to be for A2, A3, A4, and A5. All of those are just going to cancel out because the electric field isn't going through one of those surfaces. Think about the example of somebody walking by in the hallway, like we talked about in the previous video. If they're just walking by, they're not going into the room. This electric field is walking by this surface, not going in, not going out, just kind of passing by. So that's where all those terms cancel out. That's really nice, because then it's just going to be the sum of these two dot products. Well, before we get too carried away, let's take a look. This is going to be EA1 cosine of 180. This is going to be EA6 cosine of 0. Why are the angles 180 and 0? Well, for the 6 side, let's start with this one first. They're both going the same way. So think of like the alligator. The angle between that's just going to be 0 degrees. But on the flip side, over here, E field's going that way, the area vector is going the other way, so this thing is completely open at 180 degrees. And when we do that, this gives us a -1, that gives us a 1, and which means that if the area 1 is our square is equal to the area on the other side, also a square, then, oh my gosh, the total electric flux through a closed surface has to be 0. And in fact, that's going to be true for all closed surfaces. We will explore this in future videos, especially talking about with Gauss's law. But for any closed surface, if there's only field externally, it's all going to cancel out. It's only the electric fields that are inside that are going to generate a flux. And we'll explore that, as I said, more with Gauss's law. So what should we take away from this particular video? Probably one of the biggest things is that the integral form of the electric flux is just a sum of all these differential area elements that have different angles. And conceptually, you understand what that means. But mathematically, we're going to solve much simpler cases. Also, for any closed surface, only the external electric fields, as we just talked about, are going to generate a flux. If ever it's inside of the object, that's going to be what results in net flux out of the surface. Think about a classroom where, actually, it's kind of weird to have like people constantly coming out of a classroom. But let's just say it's like a hose then, for example, that if there's a leak in the classroom, it's just going to keep running out of that particular classroom door because it's always generating within it, going out. If you have, on the other hand, a hose that's squirting from one side of the room through and then out the other window, no water actually stays in the room. It's just passing through, which is what happened in that previous case. With that, I'd like to thank you for stopping by to watch this video and look forward to seeing you in our next topic about Gauss's law.